Section 9.2 covers hypothesis tests for the population mean when the population standard deviation is known. If you'll recall, when we went over 9.1, we hit some basics of hypothesis testing. We looked at what a null and an alternative hypothesis was and how to write those, how to write a conclusion. We looked at type 1 and type 2 errors. And today we're going to put it all together and actually do tests of hypotheses. Objective 1 is to perform hypothesis tests with the critical value method. The critical value method you may also see referred to as the traditional method. In the previous section, we discussed how to construct the hypotheses and write the conclusions for a hypothesis test. Now we turn our attention to actually performing the test. There are two ways to perform hypotheses tests. Both methods produce the same results. The methods are the critical value method and the p-value method. When you do a problem for me on a test, I'm going to want you to report the p-value anyway. You don't know what a p-value is yet, so don't panic, but I'll explain it when we get there. So we'll be using the critical value method, but we're also going to report the p-value. There's 6 steps we're going to go through whenever we perform a test of hypotheses. The first step is to write your null and alternative hypothesis. The second step is to determine your significance level for the test. That significance level is what we called our alpha level. The third step will be to draw a graph representing the situation. And on your take-home test, if you have printed that out already, you'll notice that I provide you with the graph and I provide blanks, so you don't have to remember all of these individual steps. I prompt you to give me this information. After you draw your graph, and make sure when you draw your graph you label your critical values. I also want you to shade your critical region when you're drawing your graph. As step 4, we're going to be going to our calculators. From our calculators we'll get our test statistic and our p-value. Using that information, then we'll draw a conclusion or make a decision. And then step 6 is to write your conclusion. These 6 things need to be on every problem where you're doing a test of hypothesis. We begin with an example. The College Board reported that the mean math SAT score in 2009 was 515 with a standard deviation of 116. Results of an earlier study suggest that coached students should have a mean SAT score of approximately 530. A teacher who runs an online coaching program thinks that students coached by his method have a higher mean score than this. Because this teacher believes that the mean score for his students is greater than 530, the null and the alternative hypotheses are as follows. We know that the parameter here is going to be a mean because we're told that in the problem. So there's our null and our alternative hypothesis. Next, we want to draw a picture and identify our critical value after we determine what our alpha level is going to be. Suppose now that the teacher draws a random sample of 100 students who are planning to take the SAT and enrolls them in an online coaching program. After completing the program, their sample mean SAT score is 562. This is higher than the null hypothesis value of 530. Here's the null hypothesis value. But to determine how strong the disagreement is between the sample mean and the null hypothesis, we calculate the value of a test statistic. I'm not going to require you to calculate this test statistic by hand, but I want you to notice what it is. Your test statistic is just a z-score, where x bar is from your data. Here we were told that x bar was 562, and the mean that we're using is the mean from the alternative hypothesis, so that would be the 530 right here. Do y'all see that? And then this is our standard error that we got from the central limit theorem. It's the population standard deviation divided by the square root of n. When we put these numbers from our data and from our hypothesis into this formula, we end up with what we call a test statistic. If you're testing a claim about a mean and the population standard deviation is known, that test statistic is going to be a z-score. We'll do this on our calculator though. Because this alternative hypothesis has a greater than, will this be a left tail, right tail, or two-tail test? Remember, the alternative hypothesis determines what type of test you have. The inequality is pointing to the right, so we would call this a right-tailed test. And if I were testing this at the alpha equals 0.05 level of significance, that means that this area right here is going to be 0.05, and I would need the z-score that gives me an area of 0.05. How do I find that critical value? Nope, all of our area is in one tail. So we're not going to divide it by 2 because the whole thing is in one tail. We only do alpha over 2 if that area is evenly split over 2 tails. We use the inverse norm on our calculator. To get your critical value, you're going to use inverse norm because it's a z-score and we know the area. The area is going to be 1 minus alpha, or 0.95, and then the mean is 0 and the standard deviation is 1. When we do this in our calculator, that gives us a critical value of 1.645. Our test statistic was this number down here, 2.76. It's way down here in this red region. This red region we call our rejection region. This shaded area right here is the rejection region. If your test statistic falls in this rejection zone, we reject the null hypothesis. Otherwise, we would fail to reject the null hypothesis. Our test statistic for this problem, we were told, was 2.76. That's this number right here, 2.76. Our test statistic falls clearly in the red zone, so our decision here would be to reject the null hypothesis. The critical value method is based on the idea that we should reject the null hypothesis if the value of the test statistic is unusual when we assume the null hypothesis is true. We choose a critical value which forms a boundary between the values that are considered unusual and the values that are not. The region that contains the unusual values is called the critical region. This critical region is where your alpha is located. So on a right tail test, all of that critical region, the entire alpha equals 0.05, would be to the right. On a left tail test, the critical region would be to the left. If it was a two tail test, we would have to split that alpha over 2 tails. Oh, F2RH naught means fail to reject the null hypothesis. Thank you for asking. This is my shorthand for fail to reject the null hypothesis. Our picture would look like this, where this is our critical value, 1.645. And our test statistic for that previous problem was way down here. It was 2.76. So that means that we would reject the null hypothesis. And then you're ready to write your conclusion. For this case, because we reject the null hypothesis, we could say that on average, students who took the coaching program scored higher than 530 on their SAT. And that's how you would word your final conclusion. One of the most commonly used values for alpha is 0.05. Alpha, remember, is our significance level. When alpha is equal to 0.05 is used in a one-tailed test, the critical value will always be 1.645. It'll be positive 1.645 if it's a right-tailed test. It'll be negative 1.645 if you're looking at a left-tailed test and you have a normal distribution. If you're using some other significance level, all you've got to do is use inverse norm on your calculator to find what that critical value is. For a left-tailed test, your critical region will be to the left. The way you can find your critical value is inverse norm. Your area will be alpha, the mean is 0, and the standard deviation is 1. If you have a right-tailed test, your critical value you can find by using inverse norm. The area now is 1 minus alpha, the mean is 0, and the standard deviation is 1. If you have a two-tailed test, you can use inverse norm alpha over 2 with a mean of 0 and a standard deviation of 1. But remember, you're going to have two answers, one negative, one positive. This will give you the negative one. Just remember, you've also got a positive one over here. The reason it works this way is because normal distributions are centered at 0 and we have symmetry. And if this area is the same size as this area, this number will be the same as this number, but just have opposite signs. Here's a table of common critical values for different significance levels. The one that we use most often will be this. The assumptions for using the normal distribution to do a test of hypothesis are going to be the same as they were in Chapter 8 when we were doing confidence intervals. We have to have a simple random sample, and either the sample size is large or the population is approximately normal. You only need one of those two. If you have a small sample, you better have a normally distributed population. Otherwise, you can't do it. There is a typo in this problem. This 399 right here needs to be changed to 404. And I'm sorry I didn't catch that before I uploaded the notes. The American Automobile Association reported that the mean price of a gallon of regular grade gasoline in the city of Los Angeles in July 2013 was $4.04. A recently taken simple random sample of 50 gas stations in Los Angeles had an average price of $3.99 for a gallon of regular grade gasoline. Assume that the standard deviation of price is 15 cents, so the population standard deviation will be 0.15. An economist is interested in determining whether the mean price is less than 404. Use the critical value method to perform a hypothesis test at the alpha equals 0.05 level of significance. As I was reading, I wrote down the important information that we needed to pull out of the problem. Now we're going to go through the process of doing a test of hypothesis. We're going to go through those 6 steps that I gave you earlier and identify all of the things that I asked you to find. We begin by finding the null and the alternative hypothesis. When you write your hypotheses, the first thing you have to do is determine what parameter you're using or testing a claim about. Will this be a mean, a proportion, or a standard deviation that we're asked to test a claim about? It's a mean. What parameter do we use for mean? Mu. One of these contains equality, one of them does not. Which one contains equality? The null hypothesis always contains equality. The alternative never contains equality. What number do we use here? Well, this right here, this symbol will be less than, but then what number do I use? 404. And we use the same number on both the null and the alternative hypothesis. Look at what they're interested in, and that gives you all of the information that you need to write your null and your alternative hypothesis. He's interested in determining whether a mean, that's why we used a mu, is less than, there's the inequality for our alternative hypothesis, 404. That's the number that we use. The next thing I asked you to do was to identify what your significance level is. For this problem, we're told to use alpha equals what? 0.05. If you're not told what alpha level to use, let that be the default. Step 3 was to draw a picture of what's going on in the problem. Because this is a normal distribution that we're going to be using, I'm going to draw a standard normal curve. So there's our normal curve. On this distribution, you need to identify where your alpha level or your critical region is going to be. Will it be to the left, to the right, or two tails? To the left, because this is a less than. So all of my alpha level is going to be over here to the left. The area right here is 0.05. What is my critical value going to be? -1.645. For step 4, we go to our calculators. This is where we identify what our test statistic and our p-value are. So to do the test, this is going to be a z-test. We hit stat, go over to tests, and the z-test you'll see is the first test. We hit enter. We don't have raw data, we have summary statistics, so we highlight statistics. Then we put in a number for the mean, for the null hypothesis, and we said that was going to be 404. Then we need to put in a number for our population standard deviation. We were told that that was 0.15, and the sample mean was 399. Our sample size was 50, and this is going to be a left tail test, so we highlight the less than, and this is what your input screen looks like, and this is what your output screen looks like. This number right here is your test statistic. It's a z-score. This is something called the p-value, and I'll explain what that means in just a minute. And then you see the mean and the sample size. So looking at this output, we would say that our test statistic is z equals -2.36. -2.36 is going to be over here. So my test statistic fell in this red region. Our p-value is 0.0092. The p-value is the area to the extreme side of your test statistic, so it would be this area. If you didn't have this program on your calculator and you had to calculate this area by hand, you would use the normal CDF, because if you know a z-score and you want the area, you use the CDF. Step 5 is to make your decision. Would we reject or fail to reject the null hypothesis based on this output? Then step 6 would be to write your conclusion. We could say there is statistical evidence to support the conclusion that the mean price for gas is less than 404 per gallon. When you're writing up your conclusion, if you reject the null hypothesis, you've proven the alternative hypothesis. Because you've proven that, and that's what our economist was interested in, we can just restate what he was interested in and our conclusion and say that we did have statistical evidence to support that conclusion. These 6 things I need to see whenever you're doing your test of hypothesis. Objective 2 is performing hypothesis tests with the p-value method. The p-value is the probability that a number drawn from the distribution of the sample mean would be as extreme as or more extreme than our observed value of x bar. In plain English, the p-value is the probability of getting the observed values, assuming that the null hypothesis is true. You don't have to memorize this or write it down even, but this is your test statistic. When we're looking at our test statistic, the x bar here is from our sample, the data that we collected. The mu sub naught is the number for the mean from the null hypothesis. The difference between the observed value and what we assume to be true is what we're looking at when we calculate this test statistic. The further away this number is from 0, the smaller the p-value is going to be. If your observed value and your null hypothesis are close to the same, there won't be much difference. Our p-value would be big and we would fail to reject the null hypothesis. But if there's a big difference between what we observe and what we assume, then odds are we're going to reject the null hypothesis because this is going to be a number that's very far away from 0. We're not going to find the p-value by hand or using tables. We're going to be using the calculator. When we do a test of hypothesis, it will always be one of the outputs for us. So don't worry about how to calculate this by hand. When you make a decision based solely on the p-value, you compare the p-value to your alpha level. If your p-value is less than or equal to alpha, we reject the null hypothesis. If the p-value is bigger than alpha, we fail to reject the null hypothesis. Up here I told you the p-value is the area, the left of the test statistic on a left-tailed test. The p-value is just the area to the extreme side of your test statistic. If that p-value is smaller than alpha, that means that your test statistic fell in the red region, the critical region. If my test statistic would have been over here, then my p-value would have been bigger than alpha and I would have failed to reject. How we get to the z-test on our calculator was we hit stat, test, and then it's the first test. We use this test if the population standard deviation is known and we're testing a claim about a mean. We use the t-test if our population standard deviation is unknown, and the one-prop z-test is what we use for proportions. Let's look at another example problem. The mean height of adult men in the U.S. is 69.7 inches with a standard deviation of 3 inches. So men's heights are normally distributed with a mean of 69.7 inches and a standard deviation of 3 inches. A sociologist believes that taller men may be more likely to be promoted to positions of leadership, so the mean height of male business executives may be greater than the mean height of the entire male population. A simple random sample of 100 male business executives has a mean height of 69.9. Assume that the standard deviation for male heights is 3, just like it was for the population of men. Can we conclude that male business executives are taller on the average than the general male population at the 0.05 level of significance? This last statement will help you write your conclusion. We begin the process, and our first step is to identify our null and alternative hypothesis. The null hypothesis, mu, equals, what number do I use for this? Not 69.9. 69.9 was the height from my sample. 69.7, because I want to know, are male business executives, these are the male business executives, taller than the general male population? Well, here's the mean for the general male population. That's the number that goes in my null hypothesis. So for my alternative, I have the same parameter and the same number. What's the inequality going to be? Greater than, because I wanted to know, are they taller than? Number 2 is to identify what? Alpha, and that's going to be 0.05. Step 3 is to draw a picture. And will my alpha be to the left, to the right, or split evenly between two tails? It's to the right. And since that area is 0.05, what is my critical value going to be? Then I need to go to my calculator so that I can identify my test statistic and my p-value. My test statistic is going to be a z-score, and it's going to be z equals some number. So we go to our calculator, we hit stat, test, z-test is the first one. I have summary statistics, so I hit enter. And what do I use for this number right here? 69.7. And what do I plug in for sigma? 3. And x bar? 69.9. My sample size was 100. I now want to use a right tail test, so I highlight greater than, and then I calculate, and this is my output. So my test statistic is going to be what? We'll call that 0.67. Typically z-scores are rounded to 2 decimal places. And what is my p-value going to be? 0.25. Typically p-values are rounded to 4 decimal places, so we'll call that 0.2525. On this graph, remember, zero's in the middle. My test statistic is 0.65. That's not quite 1. My test statistic is right here, 0.66. My p-value is this area off to the right, and that's a quarter of my graph. So what will my decision be? I failed to reject the null hypothesis because my test statistic's over here in the clear. It's not in my critical region. My p-value is huge. If the p-value is bigger than alpha, we fail to reject the null hypothesis, but I think it's easier to tell by looking at the graph that if your test statistic, what I have in green here, did not fall in this red critical region, we would fail to reject the null hypothesis. Then you need to write a conclusion. We were asked, can we conclude that male business executives are taller on average than the general male population? Our null hypothesis is that the average is the general male population. That was that 69.7. We failed to reject this. So can we make this conclusion? No. So we would say there's insufficient statistical evidence to conclude that male business executives are taller than the average man. All right, here's another example. At a large company, the attitudes of workers are regularly measured with a standardized test. The scores on the test range from 0 to 100, with higher scores indicating greater satisfaction with their job. The mean score over all of the company's employees was 74, with a standard deviation of 8. So mu was equal to 74 and sigma was equal to 8. Some time ago, the company adopted a policy of telecommuting. Under this policy, workers could spend 1 day per week working from home. After the policy had been in place for some time, a random sample of 80 workers was given the test to see whether their mean level of satisfaction had changed since the policy was put into effect. The sample mean was 76. Sample means are x bar. Assume a standard deviation is still sigma equals 8. Can we conclude that the mean level of satisfaction is different since the policy changed at the alpha equals 0.05 level of significance? That last sentence, or actually the question that I have in the brackets, will help us write both our null and our alternative hypothesis and then state our final conclusion. Our null hypothesis is going to be equals what? This was the information from before. This was the old accepted results. This is the new mean from our sample. So our null hypothesis is mu equals 74. Our alternative hypothesis will be mu is, why do you say greater than? But we don't look at that to write our null. I said look at to write our alternative. Look at this last sentence here. Can we conclude that the mean level of satisfaction is different, not equal to? Different means not equal to. See, when you're writing up a proposal to do research, you have to submit that proposal to a body to approve the research. You have to have both your null and alternative hypotheses written before you ever collect any data. This number was found only after we collected the data. We don't let this number determine anything about our null and our alternative. It's just what question are we trying to answer. That's what determines our null and our alternative hypothesis. And in this question here, or in this, yeah, it is a question, we were asked, are they different? Different means not greater than, not less than, just not equal to. Don't let this number confuse you. You only look at this last statement or the claim when you write your null and your alternative hypothesis. Step 2 is identify your alpha level. What is alpha here? Step 3 will be to draw a graph. Because I'm using a normal distribution, I'll draw a graph that's symmetric and unimodal. Is this going to be a left tail, right tail, or two-tailed test? Two-tailed. So that alpha level of 0.05 gets evenly split over both tails. That means that this critical value down here is negative 1.96 and this critical value is positive 1.96. When you do a two-tailed test, you have two critical values. One positive, one negative. How I got that number, well, I have it memorized because it never changes and I do this a lot. But how you can get this number is by using inverse norm alpha over 2 on your calculator. Step 4 is to identify your test statistic and your p-value. And we have to go to the calculator at step 4. We're going to hit stat, tests, enter. We have the summary statistics. Our mean from our null hypothesis is 74. The standard deviation was 8. X bar was 76. Our sample size was 80. And this is now going to be a two-tailed test. Our alternative hypothesis is just not equal to. Then we calculate the results, giving us this output, and our test statistic is going to be z equals 2.24. 2.24 is about right here. Your p-value is this area to the right here, as well as a matching area to the left over here. Don't worry about how I calculate it. We're told the p-value is 0.0253. You'll need to report the p-value. Whether or not you choose to use that p-value to help you make a decision is up to you, because you're going to have the picture as well. So based on this picture and this p-value, my decision is to do what? I reject the null hypothesis. And then my conclusion, we can conclude the mean level of satisfaction is different since the policy change. Because I rejected that null, that means I've proven the alternative, which says that the mean is not the same as 74. Apparently people like being able to telecommute. We can't say that it's bigger because we didn't test for that. If we wanted to claim that the satisfaction is better, then we would have to change this from a two-tailed test and make this mu is greater than 76. And that might change our results. Objective 3 is to describe the relationship between hypothesis tests and confidence intervals. In the previous example, we rejected this null hypothesis at alpha equals 0.05. In doing so, we're saying that 74 is not a plausible value for the null. Another way to express this information about the mean is through a confidence interval. Remember, with confidence intervals, we found those numbers by selecting an alpha level, and then we split that alpha level over two tails all the time. If you have a 95% confidence interval, then you use this setup here with these critical values to get the numbers for this confidence interval. Because 74 is not in this range of values, we say that 74 is not plausible, and that would lead us to reject the null hypothesis. The three dots mean therefore. Because it's not a plausible value, we can reject that null hypothesis using a confidence interval. Confidence intervals can be used anytime you have a two-tailed test. If you have a one-tailed test and you want to use a confidence interval, you have to double the area to get the same results. Objective 4 is to describe the relationship between alpha and the probability of error. Remember when we went over type 1 and type 2 error in 9.1, I told you that alpha was equal to the type 1 error. The type 1 error is the probability of rejecting a null hypothesis when it's true. That's what alpha represents. I also told you that as alpha increases, beta, the type 2 error, decreases, and vice versa. As alpha decreases, beta, the type 2 error, will increase. There's this inverse relationship between the type 1 and the type 2 errors. The type 2 error is the probability of failing to reject a false null hypothesis. We want both of those to be as low as possible. But I went over those in great detail on 9.1. I'm not going to spend a lot of time on those tonight. Objective 5 just tells you that you should report the p-value or the test statistic value. I'm telling you it's good practice to report both the p-value and the test statistic. Sometimes people report that the test result was statistically significant at a certain level without giving a p-value. It's much better to report the p-value along with the decision whether you reject. There's two reasons for this. There's a big difference between a p-value that's just barely small enough that would cause you to reject the null and one that's way small. We would feel more confident with a p-value that was really small like this versus a p-value that caused us to just barely reject the null hypothesis. Best practice is report both the p-value and the test statistic. Objective 6 is to distinguish between statistical significance and practical significance. When a result has a small p-value, we say that it is statistically significant. Anytime we reject the null hypothesis, that just means that we have statistical significance. That may not mean that we have practical significance. For example, a new study program may raise student scores by 2 points out of a 100-point scale. This improvement may have a statistical significance, but the improvement may not be enough to offset the cost of training teachers. So if it costs the district $100,000 to implement this new program, but they only expect to see a 2-point increase in test scores, they may not want to spend that money just for 2 points. In that situation, we wouldn't have a practical significance. And that's where common sense comes in. This wraps up section 9.2.